Bayes formula. It sounds like you did this Monday, and I wasn't prepared for you. I'm prepared now. So we talked about conditional probability like really briefly right before you took your midterm. And then I had like another side of a handout that I said I'm going to skip it because she hadn't gone over Bayes' theorem yet. So we'll go back to the other side of that handout that I skipped from before. But I'm going to start with kind of a review of how the formula works. So when we say conditional probability, that's where you have that line down the middle and we say given. So if I read that first line there, it says the probability of A given B is equal to the probability of A and B divided by the probability of B. Well, there's another way I could write that also has conditional probability in it. I could write it as the probability of B given A times the probability of A divided by the probability of B. So these two formulas there, they're equivalent to each other. And sometimes we have some of the information and it would make one version of that formula better than the other. But neither of them are perfect if in the particular situation, we don't have the thing in the bottom, because both of those formulas rely on us having the probability of B. And if we don't have the probability of B ready to go, we have to go find it in a different way. So that's the next line. If the probability of B is not given, we can actually break up that bottom into an even more complicated looking bottom piece. But even though it looks more complicated, sometimes those are things they've given us in the problem. So if they've given us those more complicated looking pieces in the bottom, it actually makes the problem easier. I know that seems really weird, but it all depends on what they gave us. So in the bottom, it says, if we don't have the probability of B, we can actually get the probability of B using this right here is called the law of total probability. It says, if you have the probability of B and A plus the probability of B and A complement, or another way you could say that is not A, then something kind of funky happens where if you have the A and you have the complement of A over here, they kind of cancel each other out, and that's why that becomes the probability of B. So it's a weird statement, but if you take like actual like examples of things with those Venn diagrams and stuff again, you'll see that it's true. And so a way that we can put this back, so you see how like that one we could turn into a conditional probability statement. They just did the same thing here where they had these with the ands in the middle and they turned them back into the conditional probability versions of the same thing. Why do I have all these on this like top of the page? Because these are not things that are easy to memorize. So I'll be like right in the middle of a problem with you guys and I'll go, shoot, okay, there's a formula. And so it's nice to have them written out like this when we go through Bayes' theorem problems. But the main thing, how do I know it's a Bayes' theorem problem? Here's how I know it's a Bayes' theorem problem. If what they're asking us in the problem is for the opposite of what I see, like they've given me in the problem A given B, but they're actually asking me for B given A, then I know it's a Bayes' theorem problem. So it's always like you have the backwards of the thing that they're asking you for. And so you're like, ah. Then I go, okay, cool, that's going to be Bayes' theorem. So I'll give you an example. Drug testing. Woohoo! Such a cheerful topic, right? All right. I'll zoom in a little bit. Drug testing in athletes. When Olympic athletes are tested for illegal drug use, which they call doping, the results of a single test are used to ban the athlete from competition. The University of Texas biostatisticians demonstrated an application of Bayes' rule to making inferences about testosterone abuse among Olympic athletes. Okay, lots of words there. There was nothing in there that was useful to us yet. The next line is where we start getting useful stuff. They use the following example. In a population of 1,000 athletes, suppose 100 are illegally using testosterone. Of the users, suppose 50 would test positive for testosterone. Of the non-users, suppose 9 would test positive. Okay, is your mind blown yet? Because like, I hadn't really thought about this until I was reading problems like this. They just said of the non-users, these people aren't using testosterone. 9 of them still tested positive. So what's the problem with some of these like doping tests? They're not perfectly accurate, right? So you could get in trouble for doping and you're not. 9 of these people weren't doping and it still said they were. So that's why they'll sometimes challenge those things and they'll go and they'll get another test, because the chances that 2 tests say that you're doping and you're not, pretty slim. But every test has some error built into it. And so I actually didn't really think about that. Like every time you go to the doctor and you get like a blood test or whatever and they're checking for something, I just sort of trusted that that like is accurate. But the truth is, lots of blood tests have error built into them. And so sometimes I've gotten like test results that were abnormal and I've like been all freaked out. And then I go see my doctor and they go, let's just draw it again. And then the test comes back totally normal. And so they're like, fine. And I'm like, but what about the other one? And they're like, oh, that happens sometimes. And I had never really thought about the fact that like a blood test could lie. Like what? But there's error in everything. Why is there error in it? Humans are actually in a lab dealing with your blood, so stuff could go wrong. Anybody into like true crime stuff? Like the numbers of mistakes that they make in like those labs when they're doing the DNA analysis, and they're all like, oh, we found this person's like DNA all over, and then they're like, oh, oops, we had 2 bodies in the lab at the same time and we accidentally swapped some whatever, and so something spilled on this, and so this other guy got accused of a crime, and you're like, I never even thought about that, because you're like, the DNA shows they were there. And you're like, yeah, but there's human error that happens. And so sometimes people have to challenge test results. I'm like, oh, okay. So that's my long-winded way of saying, sometimes when they ask these problems, the reason that it's interesting is that just because you have a test result that says something is the case, doesn't necessarily mean the test is telling you the truth. So there's different words that we say for that. When we talk about the first thing here, says, given that the athlete is a user, so the athlete is doping, find the probability that the drug test for testosterone will actually say they're doping, will actually yield a positive result. So if they are doping, what's the probability the test will actually correctly say they are? That has a special word in drug testing, and it's called the sensitivity of the drug test. But then we have this other thing. If we look at question B, it says, given that the athlete is a non-user, so they're not doping, find the probability that the drug test will yield a negative result. So this is saying, given that we know they're not using testosterone, what's the probability the test will accurately say they're not using it? That has a different word. That's called the specificity of a test. So we actually test for both in the land of like pharmaceuticals and drug tests and that kind of stuff. They care about both of those things, the sensitivity and the specificity. Okay. When we do problems like this, we first want to see what they gave us. So I'm going to go back to the line where they gave us important information, and I'm going to see if I can write it in like that probability notation. We'll see what we have. So the first thing they said is, in a population of 1,000 athletes, suppose 100 are illegally using testosterone. Okay, so are you okay with me saying the probability of capital T, that means the probability that they're actually using testosterone? So I'm going to use capital T to say they're using it. Okay, the probability they're actually using it, if we have 1,000 athletes and 100 of them are, what we want to write is the 100 in the top and the 1,000 in the bottom. And there's nothing wrong with that number, but we usually turn it into a decimal now. If you didn't have a calculator, could you turn this into a decimal? Here's what Jen would do. I'd start crossing out zeros in common. So there was a 0 in common, and then I got another 0 in common, but now I've run out of zeros in common. So what I ended up with was 1 in the top and 10 in the bottom. 1/10 as a decimal is 0.1. I did it without a calculator. Go. Okay. The next thing says, of the users, suppose 50 would test positive for testosterone. Okay. So that's actually what they're asking us down here, but we'll get to that in a second because I just said, let's figure out what they've already told us. So they've said of the users, so probability, this is going to be conditional probability. So they're saying, given that we know they're a user, so I'm going to put the line down and put a T there. They're using testosterone, given that I know that. Suppose 50 would test positive. So I'm going to put a plus sign to say they're testing positive. So I'm saying, given that I know they're using testosterone, this is the probability that they test positive. Okay, so my denominator this time shouldn't be 1,000. What should my denominator be? Because it says of the users. Yeah, 100. Because it says there's 100 users. So my denominator this time is going to be 100. It said of the users, suppose 50 would test positive. So 50 goes in the top. So 50 over 100. Again, you could cancel out zeros in common. That would be 5 out of 10, which is 0.5. All right, they gave us one more piece of information. It says of the non-users, suppose 9 would test positive. Okay, so I've been using T for users. What should I use for non-users? Yeah, T complement. So you guys can either put the little dash or the little C. I'm going to put the little C because for me, that's more clear. It's a complement, but the dash is also fine. So it says of the non-users. So that's given that we know they're a non-user. So I'm going to put the line down and put the T complement after the line. Given I know it's a non-user, we're talking about them testing positive. So I'm going to put the little plus sign in front. So the probability that they test positive, given that I know they're a non-user. What's my denominator for this one? So how many athletes were there total? 1,000. How many were using? So 900 should be our denominator, right? Good. 900 is our denominator. And it says that 9 of those tested positive. So we're going to put 9 over 900. Is that okay? I can't cancel out any zeros in common on this one. So what's happening is you are dividing by that 900, and that's going to give you 0.01. And we've now written down everything they gave us. So we're going to go through the questions now, and we might already have some of the answers from what we've done. So sometimes that's a nice bonus. So first one says, given that the athlete is a user, so given that they're using testosterone, find the probability that a drug test for testosterone will yield a positive result. So they're asking for the probability that it tests positive given that they're actually a user. We already have that number. We figured that one out was 0.5. So we don't need to do that one again. So that's why I like putting down everything we've already got. Sometimes we get answers for free. Let's look at the next question. Given that the athlete is a non-user, so we're going to put given and we're going to put T complement. Find the probability that the drug test for testosterone will yield a negative result. So this time, instead of putting a little plus sign, I'm going to put a little minus sign. Or you could put a plus sign complement if you'd prefer, because those mean the same thing. So whichever your preference is. I'm going to put a negative, just, I don't know, feels like that's more clear. All right.
On our list of things we have, that is not one of them. Okay. However, it is a thing we can get if we're clever. So we're talking about the group of people who are not using testosterone. But we're talking about the group of people who actually are testing negative. We have the number of people who were not using testosterone who tested positive. The number of people who were not using testosterone who tested positive, the only other option is that they tested negative, right? So there's two options. So if I have the number for however many of them tested positive, could I get the number who tested negative? Yeah, it should be the complement of what we've got. So I can do 1 minus this 0.01, and that should give me the answer to this. So I'm going to say 1 minus the probability that we tested positive, given that they're a non-user, because that's what I already have. So I have 1 minus the 0.01. Which comes out to be 0.99. Not too bad yet. None of these have required Bayes' theorem yet. But the last one will. If an athlete tests positive for testosterone, use Bayes' rule to find the probability that the athlete is really doping. Okay. So what they're asking us for is they're saying, given that you found out that they tested positive, so that means given it was a plus sign, given you got a plus sign, what we want this time is the probability they were really doping, which means they really were using testosterone. Here's how I know that's a Bayes' theorem problem. We have plus given t, but they're asking us for t given plus. If they're asking you for the opposite of the thing that you have on the paper, Bayes' theorem. So we got to flip them around. To flip them around involves that fun formula that's at the top over here. What I'm going to do is I'm going to use this ugly one down at the bottom. Why am I going to use the ugly one down at the bottom? Because in this problem, A given B, I have to have the B, I have to have probability of B to answer the question, right? So if they're saying that's the A and that's the B, I have to have the probability of a plus somewhere. But if we look at the list of things that I have the probability of T, I have the conditional probability here, and I have another conditional probability. I don't have the probability of just a plus. So I can't use the top formula where we just have the probability of B in the bottom. That won't work. I got to use the more complicated one. So I'm going to use the more complicated one. I'm going to write out what that's going to look like when we substitute in the T and the plus for the A's and the B's. Okay. So here's what that's going to look like. It's not as hard as it sounds. Okay. Here's what you're doing. If you have this, I want the opposite of that. So I'm going to write the probability of plus given T. So I'm just turning it around. Times, and we always end up multiplying by the probability of what's in the bottom here. So I'm going to say times the probability of T. Okay, so again, to start, when you're doing a Bayes' theorem one, whatever they gave you, switch them. And then whatever comes second, that's the thing that goes as the next probability. Okay, now here's the weird thing. You're going to put a big old division bar like that. And in the bottom, you're immediately going to write what you just wrote right here. So exactly the same thing goes right here. So we're not even thinking yet. We're just copying what we just wrote. Okay, and then here's the part that gets a little bit tricky, but not too tricky, I promise. Okay, you're going to put a plus sign now. And then you're going to put the probability of plus. So we're still going to start with the plus, But then after the given line, you're going to put T complement. Okay. And then we're going to multiply by that second thing right there. The probability of T complement. And you're done. That's the formula. So, to repeat, when it's Bayes' theorem, the very first thing you do is flop what they gave you. And then whatever is the second thing, you multiply by the probability of that second thing. Okay. Then you immediately take the thing you just wrote and put it down here and put a plus sign. And here's the part that's just a little bit trickier. Whatever that is, that stays there. And then whatever the second thing is, you put the complement of that thing. And then you always multiply by whatever the second thing is, right there. Do you have to have it memorized? No, because she's probably going to put it on a formula sheet for you, but just, it makes it a little easier if you already know where we're going with it. All right. On my list of things that I have, probability of plus given T. I have that one. Probability of plus given T was 0.5. Yeah. Okay. Probability of T. Yep, I got that one. I obviously, since I just put the exact same thing here, I have both of those as well. So now I just have to check out this one. Do I have plus given T complement? Plus given T complement? Yes, 0.01. So the only thing I don't have is the probability of T complement. But is that a problem? Nah, because we have the probability of T. So the probability of T complement is just 1 minus this number. So I'm going to write that right here. Probability of T complement is going to be 1 minus the probability of T, which we have. We said that was 0.1. So 1 minus 0.1 should be 0.9. So we literally have all the numbers we need. We're just going to plug them in. All right. So probability of plus given T, we said was 0.5. Probability of T, we said was 0.1. In the bottom, we're going to write exactly what I just wrote, 0.5 times 0.1 plus. All right, and now we need plus given T complement. That one is 0.01. And finally, our probability of the T complement, we said was 0.9. Probably on her test, she'll have you just leave that there and put the little star after it. But since I have a calculator, we might as well find out what it is. Okay. Right, this came out to be 0.847. So if I rounded that, that's approximately 0.85. So what does that mean? It says, given that we know that the athlete tested positive, so you've got a group of athletes in the room, you've called them all in because they tested positive, so they're all in trouble. The probability that they actually did the bad thing, given that they tested positive, is only 85%. So 15% of the people in the room that you've called in got falsely accused of doing a bad thing, and this is for realsies. So this is why it's important to have people who understand statistics in the room to go, cool, let's test them all again, because the probability that both tests are going to say that they doped if they didn't, very, very small. But the probability that the first test is going to maybe give a result that could get some people in trouble. I mean, that's kind of surprising to me that that many people could be, you know, the 85% of them really did do the bad thing. But there's people in that room that are getting in trouble for no reason. I think it's interesting, but I also know I'm a total dork, so it's okay. You don't have to actually think it's cool. I'm going to go back to a handout I gave you previously. I didn't make extra copies of it. I apologize, but I will make, when I go, I'll scan stuff at the end, so it'll be in Canvas, even if you don't have a copy of it later. Don't worry, I promise you'll get a copy of it. This was from the handout that the first side of the handout said probability practice, and we did that one. It had the survey of American workers who had the retirement plan and insurance. I did the front side, but I skipped the back side because it had Bayes' theorem on it. We're ready to do Bayes' theorem now, so we'll do the back side. And again, if you don't have it, I promise I'll post a scan. I actually already have the answer to this scanned in there already. So some of you might be like, I did this already, Jen. Good job, you. If you didn't, that's okay. All right. We know the likelihood of a particular crime being committed is 2%. So I don't know what crime this is. Murder. Sure, let's go with murder. If a person really did commit the crime, the probability they're found guilty is 99%. So if they really did commit murder, they have a 99% probability of being found guilty. That's great. If they did not commit the crime, they are 98% likely to be found innocent. That's not so great. They did not commit murder, and we're only 98% probable that we're going to actually correctly say they're innocent. So the justice system has some flaws, and that's why there's always people who are going through appeals for their cases and different stuff. Okay. So before we jump into the questions, Jen likes to write down what they gave us. So let's see, I'm going to write it at the top because I need a little more space. The likelihood of a particular crime being committed, so we're going to say probability of that crime is P of C. Instead of 2%, we're going to write it in its decimal form, 0.02. Okay, that's the first thing we got. If a person really did commit the crime, so that means given they committed the crime, so I'm going to say, given they committed the crime, the probability they're found guilty, we'll use G for that, is 99%. So we're going to write that as 0.99. They gave us one more thing. If they did not commit the crime, so given they didn't commit the crime, so I'm going to put capital C with a little c for they didn't commit the crime. Given that C complement, they're 98% likely to be found innocent. So I'm going to put guilty complement. But if you wanted to use an I for innocent, you could also do that. I'm just going to use the complement notation since I went down that road. 0.98. All right, that's all the information they gave us. So everything else we're going to have to find. Next, find the probability that if a randomly selected adult is found guilty, they actually committed the crime. So given that they're found guilty, so I'm going to put the given guilty, they actually committed the crime. That's probability of C given G. All right. How do I know this is a Bayes theorem problem? Yeah, I have that one, but they're asking me for backwards. So I'm like, cool. All right. So Bayes theorem, the way we start it, we write the opposite of what they gave us. So we're going to say probability of G given C times, and then it's always the probability of the second thing. So probability of C. Then I put the big old division bar. And I immediately write what I just wrote down here at the bottom. So I just wrote probability of G given C times the probability of C. So haven't done any thinking yet. All right, now I need a plus sign. And then we're going to do probability of G again. We're going to write probability of G, but then after the given bar, we're going to put C complement. Okay. And then we always do times the probability of the second thing. So it's probability of C complement. All right. In terms of what we've got, G given C, I have that one. Probability of C, I have that one. So that means I have both of those too, because I just wrote the exact same thing down. Probability of G given C complement, I don't have that. I have G complement, C complement, but that's okay because this is all the people who did not commit the crime. The people who did not commit the crime, who were found innocent, was 98%. So if they did not commit the crime, what's the probability they were found guilty? The complement of that. So we're going to do 1 minus that. So I'm going to write that right here. Probability of just guilty given C complement should be 1 minus 0.98, which is 0.02. And then there's one more thing in that formula. It says probability of C complement. I don't have C complement, but I do have C. So I can find C complement. Probability of, whoops, C complement should be 1 minus 0.02. So that should be 0.98. Let me fix that parentheses. It's going to bug me. There we go. Cool. Now we have literally everything. We just have to plug it all in. So probability of G given C is 0.99. Probability of C is 0.02. We're going to write down exactly the same thing right here. Plus, and then probability of G given C complement, we just figured out was 0.02 times the probability of C complement, we just figured out was 0.98. Okay. So probably on her test, she'd have you just leave it there. But again, I have a calculator, so we might as well figure out what it really is. Okay, this came out to be 0.503, which is approximately 50%. Whoa. Okay, so this says, given that they actually were found guilty, so they were in the courtroom and they said, you're guilty, you're going to jail. The probability they actually committed the crime, 50%. So this is why they have appeals and all that kind of stuff when we're doing court cases. Now, again, we made up a percentage for this particular crime. So none of these are actually like real numbers for a particular crime here. We made this up, but errors do happen. And when we use these sort of conditional probability rules, it helps to have statisticians who can understand probabilities of things might lead us to make mistakes. and we need to sometimes have retrials or look at evidence again. Find the probability that a randomly selected adult is found guilty and they actually did not commit the crime. Okay, so probability that they're found guilty. So given that they're guilty, that they actually did not commit the crime. So I'm going to put C complement there. Oh, I actually totally wrote that wrong because it's not a given, is it? Jen. What word did they use in the middle? And Jen did that wrong. I'm going too fast. I'm too excited. Slow down, Jen. Okay. Find the probability that a randomly selected adult is found guilty and, okay, found guilty, and I need my upside down U, my intersect, and they did not commit the crime. There we go. That's what I wanted. Sometimes I think too fast and then I do silly things. All right. You've got a formula for your and symbol. That lets us turn it into a conditional probability. So here's what the formula says. This is the probability of G times the probability of C complement given G. And so sometimes that's all we need. And we go, awesome. So then we look up here at what we have and we go, do we have the probability of G anywhere? Nope. And do I have the probability of C complement given G? And we look up here and we go, no. I actually have neither of the things that the formula says I need. And sometimes that means we got to go do a crazy other formula. But sometimes it means we've got to look at what they said here again. And because that's an and symbol, it's okay for me to turn that around. I could also write this as the probability of C complement and G. Because with an and, you're allowed to flop where things are. If I have a dog and a cat, I have a cat and a dog. That doesn't change anything. So I can turn those around. And if I turn those around, that also changes the formula to the probability of C complement times the probability of G given C complement. And here's what was cool about that. By me just turning that around and writing it again, probability of C complement is actually on my list. I have that one. And probability of G given C complement is also on my list. So now I have both of those things. And so sometimes when you're doing the homework problems, before you panic, see if there's a thing with like an and symbol where you could turn it around. Because sometimes it just means we got to turn the thing around. So this was okay, but I'm going to put a bit of or here because it didn't end up being helpful. I redid it, and now this is totally helpful. I have both of those numbers. Probability of C complement, we said was 0.98. And the probability of G given C complement, we said was 0.02. And so we didn't have to go do anything crazy. We have those. So 0.98 times 0.02 comes out to be 0.0196 or approximately 0.02. So the probability that a randomly selected adult is found guilty and they actually did not commit the crime is about 2%. Not great. Not terrible, but not great. Last one one doesn't involve Bayes' theorem. It just involves us going back to our definition stuff again. Are the events guilty and committed the crime independent or dependent? Justify your answer mathematically. Did you have a question like that on the midterm? So we got to remember that the definition of independent events is the probability of A and B is equal to the probability of A times the probability of B. That's the definition. So if that comes out to be true, then it means they are independent. And if it comes out to be false, then we say they're dependent. So in this case, we would be using G and C instead of A and B. So we need the probability of G and C. G and C. Do we have G and C? We do not. But we can go get it. How can we go get it? Well, the reason we can go get it is that we have the probability of G and C complement here. And so we could find, let's see, the probability of G. Okay, sorry. We don't need to use that one. We can just use our definition of G and C. So that's the probability of G given C times the probability of C. That's just using our definition. Because we have G given C and we have the probability of C. All right. So G given C was at the top of our paper. We said that was 0.99 and probability of C we said was 0.02. So we're just plugging those in. So 0.99 times 0.02 comes out to be 0.0198. And I'm not going to round that one because we're actually trying to make like an equality formula. So we need this to equal the probability of A times the probability of B. And in this case, that means I need the probability of G and C to be equal to the probability of G times the probability of C. So we just figured out the G and C part. So now we need the probability of G times the probability of C. And if this comes out to be 0.0198, then yes, they're independent. And if it doesn't come out to be 0.0198, then they're not independent. We could say they're dependent. So probability of G is not a thing that we have calculated. Probability of C we do have. So we have to go find the probability of G, and that's using our law of total probability. So we need this one. So we're going to do that calculation here. The probability of G is equal to the probability of G given C times the probability of C plus the probability of G given C complement times the probability of C complement. This is our law of total probability, which we have on the formula page up here. So if we want the probability of B, we break it up into those things, which is what we just did. All right. So probability of G given C is 0.99. Probability of C is 0.02. Probability of G given C complement, we have 0.02. And the probability of C complement we said was 0.98. So we have all of those. So that's going to let us find the probability of G. Right, and that came out to be 0.0394. So we found the probability of G, 0.0394. We need to multiply it by the probability of C, which is 0.02. And we're checking to see if that answer is the same as 0.0198 or if it's not. So 0.0394 times 0.02 comes out to be 0.000788, which is definitely not the same. Okay, so here's the deal. These are not the same. Okay, because they're not equal, that means that these are not independent, or we could say they are dependent. So guilty and committed the crime are dependent based on our definition. There's a reason I held off on that example. It's hard. It involves all the formulas and all the things that can go wrong where you get into one of them and you're like, shoot, we don't have that. So if you were like going through that and you're like, I'm more confused than I was before, Jen, the first example you did for Bayes' theorem wasn't nearly as bad. That's correct. So I made you the separate handout on Bayes' theorem stuff. The stuff that we started with today, that's probably the level she wants you to be able to do for exam type stuff. But occasionally on the homework, she throws these trickier ones at you. So I wanted to give you one that was a little bit harder in case when you're doing the homework, you're like, what? So that you know, oh, I probably need to go hunt for one of the other formulas that are at the top of that page. So I gave you all the different ways that you might end up needing to use it. It might be helpful on the homework. So some of the homework problems can be tricky. I haven't seen the homework problems, but in the past, I have known them to be slightly tricky. How you doing? Ready to just like change over? Bayes' theorem's kind of, there's a lot. Let's switch over to binomial probability practice. I tried to make this kind of sort of match up with the notes that got sent my way. So thank you for sending me notes. That makes it helpful. But I tried to make them slightly different so that you would have some additional practice that sort of looked like what she did. I'm not gonna lie, I hate the probability stuff. Personally, it messes with my head. My brain does not naturally work in the probabilities. When we go back to the statistics stuff, my brain is much happier. So if you're one of those people who's watching the probability stuff and you're like, this stuff's tricky and I hate it, that's okay. We'll get through it. If you like this stuff, wow, that's awesome. Some people love the probability stuff and they end up like probably like being the ones making the money in Vegas and all the other stuff if they're good with the probabilities. I'm terrible with probabilities. So I don't find most of this stuff to be intuitive. My brain doesn't like it, so I actually need the formulas and things to look at. If you're like that, that's okay. You can still survive it. She picked a 6-sided die that had like G's and
It was like, yeah, G's and R's. I made this very similar, but the numbers are different and the things are different letters, okay? So we're gonna try and use pattern matching to figure out what we should do. A fair six-sided die has 4 sides labeled S for successes and 2 sides labeled F for failure. I chose those specifically because when we're talking about binomial theorem problems, we talk about probability of success and probability of failure. So I was trying to be a little like symbolic here. So we got successes and we got failures happening. Okay, you're gonna roll that die 3 times, and each roll is independent. Independent means what I got on the last roll has nothing to do with what I'm gonna get on the next roll. It's a fair die. Getting one result the first time doesn't change what's gonna happen the second time. Every time I roll it, equally likely to get any of the results that I was on the first try. Let a roll showing S be considered a success. Okay. What is the probability of getting a success on a single roll? So we're only rolling 1 dice this time. And if it's 1 dice, we say 1 die. Okay. So I roll it. What's the probability I'm going to get an S? 4 out of 6. My brain can do this one. The next ones are where my brain gets unhappy. Okay, so on a single dice roll, because there are 6 sides and 4 of them have S's on it, your probability of getting a success on a single roll is 4 out of 6. It's also okay for you to turn that into 2/3 if you want. It's also okay for you to turn it into a decimal. It's also okay for you to turn it into a percentage. I'm going to leave it at 2/3 though, because the way we're going to do the following problems. Just simplifying the fraction makes the math a little better. Okay. Use the binomial distribution to find the probability of getting exactly 2 successes on 3 rolls. Okay, so we got this formula, I assume. I'm going to write down a formula and you can tell me whether it looks familiar or not. Probability of K is equal to N choose K times the probability of a success. For a success, we use P and we raise it to the power of K. And then Q is often what we'll use for a failure. And we raise that to the power of N minus K. There's another way we write this formula sometimes. Instead of putting the Q's in there, what we write instead is 1 minus P, because 1 minus P is the same thing as the Q. So both of these formulas are equivalent to each other. Sometimes they use P's and Q's, and sometimes they just use P's. When she did hers, did she use P's and Q's or just P's? Or did you not see this formula yet? Not sure. No idea. She hasn't shown it yet. All right, I get to win. Yes.
She briefly mentioned the N over the K part we talked about it not having a line between it, but didn't really go through the whole.
Sweet. Okay, this is exciting. I get to be the first person to show you this. Woo! Okay. This is a weird math thing, and it's called a combination. Did she say that? There's things called permutations, and there's things called combinations. For this one, we're doing a combination, and the formula involves those factorial things I talked about last time. So that was why I introduced the factorials. So this part right here, the N choose K, is a combination. And here's what it actually wants you to do. When you see N choose K, there's going to be numbers in there. And the number on the top is going to be the N, and the number on the bottom is going to be the K. And what you're going to do is you're going to take the top number and put a factorial after it. Then you're going to put a division bar. You're going to take the bottom number and put a factorial after it. And then you're going to take
the top number minus the bottom number in parentheses, and then put a factorial after the parentheses. That's what that n choose k, and that's how we actually say it. So I'll write off to the side the words that I'm saying. N choose k. And I'll put quotes around it because when you see that, people will say n choose k. It just means the n's in the top, the k's in the bottom. So that little part of the formula, we normally have to calculate separately, and then we go back to the rest of the formula later. The P up here is the probability of a success. And the Q up there is the probability of a failure. And again, we don't have to use a Q. We could do 1 minus P. Whenever we're using the binomial distribution, it means only two things can happen, one thing or another thing. So the probability of a success, if you want the probability of failure, it's just 1 minus whatever the success was. So that's why there's two formulas. You can either write the Q or you can just put 1 minus P and you don't need to have a Q as a separate thing in there. They mean the same thing. Okay. In this problem, the getting an S is considered to be a success. Okay. So it says, use the binomial distribution to find the probability of getting exactly 2 successes in 3 rolls. The N is the number of rolls and the K is the number of successes. So what we're doing in this problem, the probability that we have 2 successes, so I'll say K is equal to 2, is going to be the total number of rolls was 3, and the number of successes we're asking about is 2. So we're going to say 3 choose 2. So that took care of this part of the formula. Now I need to put the probability of getting a success. We did that in part 1. The probability of getting a success for a single roll was the 2/3. So that's where that P is going. That's a 2/3. So notice 3 choose 2, there's no line there because that's not a fraction. That's actually a separate formula. But here, the 2/3 is a fraction, okay? What we always do is we raise the probability of success to the power of whatever K is. So in this problem, our K is 2. So we're going to say 2/3 to the second power. Now we need to put the probability of a failure. If the probability of a success was 2/3, what's the probability of a failure? 1/3, perfect. It's always 1 minus the probability of a success. So 1/3 goes there. And then we raise that to the power of n minus k. So in this case, that's the n and that's the k. So 3 minus 2. Ta-da! There's our formula. Okay. So in order for us to do this, I need to figure out what 3 choose 2 is using this formula right here. So I'm going to do that off to the side. I'm going to go figure out what 3 choose 2 is. 3 choose 2 is equal to the top number factorial divided by the bottom number factorial times, in parentheses, 3 minus 2 And on the outside of the parentheses, you put a factorial. So last class I said factorial means whatever that number is times all the numbers smaller than it. So 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1. And then in parentheses, we've got 3 minus 2. That's just 1 factorial, but that's just 1. 1 factorial is always 1. So we have 3 times 2 times 1 in the top. We have 2 times 1 times 1 in the bottom. So 3 times 2 times 1 is 6. And in the bottom, 2 times 1 is just 2. So we have 6 divided by 2, which is 3. What is that? That number 3, we just substitute in right there for that piece. So this thing right here, we did a little side note and we figured out that that's 3. Okay. So that was 3. 2/3 squared means 2/3 times another 2/3. Are you okay with that being 4/9? 2/3 times another 2/3. You do the 2 times 2 and you do the 3 times 3. So it's going to be 4/9. And then 1/3 to the power of 3 minus 2. That's just 1/3 to the first power, which is just 1/3. So we got to multiply 3 times 4/9 times 1/3. If it helps, put that 3 over a 1 so that you can see it's got a denominator as well. And so we have to multiply all the numerators together and then all the denominators together. 3 times 4 times 1 is 12. 1 times 9 times 3 is 27. So we got 12 over 27. That's totally fine as an answer, but both of them are divisible by 3, so I can actually simplify that. So if I say 12 divided by 3, I'm going to get 4. And if I do 27 divided by 3, I'm going to get 9. So in most simplified form, we'd get 4/9. So the probability of us getting exactly 2 S's when I roll all 3 of the dice would be 4/9. These other ones require us to not use that formula, and we have to go back to some of the probability definitions that I'm really bad at. What is the probability of getting at least 1 success? In this case, 1 success is if I roll 3 dice, I could get 1 S, I could get 2 S's, or I could get 3 S's. I need all of them. So what that ends up being is the probability of at least 1 success is equal to 1 minus the probability of 0 successes. Because at least 1 means I could get 1 or 2 or 3. If I want to do it that way, I have to calculate the probability of getting exactly 1. I have to calculate the probability of getting exactly 2, which I already did that one. We got 4/9 when we did that. I'd have to also do the probability of getting exactly 3. So we would have to use this formula 3 times, and then we would have to add those things up. Or if we recognize that the probability of getting at least 1 is the same thing as the complement of 1 minus getting none of them, then we have less we have to do. So it is possible to do it the other way, but we would need to use this exact formula that we used for 2. We'd have to do it for 1, for 2, and for 3 and add them up. But it's going to be easier if we just do 1 minus the probability of getting none of them as an S. Okay. So the probability that none of them is an S, we didn't actually talk about that as a separate problem up here, but the probability of getting a success on a single roll what's the probability of getting a failure on a single roll? One third, right? Because the probability of a success is the complement of a failure. So it would be 1 minus this 2/3. So probability of a failure is 1/3, because they got to add up to 1. Okay. They didn't ask for that for this part of the problem, but if we know that the probability of success is 2/3, then the probability of a failure is 1/3. Then probability that I got 0 successes on all 3 rolls is going to be this. 1 minus 1/3 would just be if it was 1 roll. 1/3 times 1/3 would be if it was 2 rolls, and 1/3 times 1/3 times 1/3 would be if it was 3 rolls. So it's 1/3 to the 3rd power is how we write that one. So this would be 1 minus 1 over 3 times 3 times 3 is 27. So I could rewrite that 1 as 27 over 27 minus 1 over 27. That's going to give us 26 over 27. So if I roll all 3 of those dice, and every single one of those dice has 4 S's on it, the probability that I'm going to get at least 1 S after I roll all 3 of the dice is 26 out of 27. We got pretty good chance I'm going to get at least 1 S when we do it. That's very different than asking what's the probability you get exactly 1 S. If we wanted exactly 1 S, we got to go use this formula. So if you think about how they wrote this one, they said use the binomial distribution to find the probability of getting exactly 2 successes. That was us using the binomial. But because it said at least 1 success, we had to think of probability of getting exactly 1 and exactly 2 and exactly 3 and adding those all up. Or we did the complement of that, which ended up being faster, where we did 1 minus the probability of getting none of them with an S. Okay. The last one says, what's the probability that all 3 of them are going to roll out successes? So you roll all 3 dice and you get an S on the first one and an S on the second one and an S on the third one. That's different than saying, what's the probability of getting exactly 3 successes? If they said exactly 3 successes, we'd have to use the binomial theorem, but we're not doing that on this one. If it's exactly 3, we need that formula. If it's all 3, the probability all 3 successes is going to be the probability that you got a success, which in part 1, we said the probability you got a success was 2/3. That's for the first die. And it would be 2/3 times 2/3 if you were rolling it twice, but you're rolling it 3 times. So it's going to be 2/3 to the 3rd power. So 2/3 to the 3rd power is 2 times 2 times 2 in the top. That's an 8. And 3 times 3 times 3 in the bottom. That's a 27. So the probability that you would get all 3 of them an S if you roll all 3 of the dice is 8 out of 27. So she did one that was like that, and then she did one that was like multiple choice questions, and she often reuses that one. So I took a similar one. There's a different number of problems, but same idea happening here. A student randomly guesses at 7 multiple choice questions. So they did not study at all. They have no idea. They can't even narrow it down. They're literally guessing. Each question has 4 possible answers with only one correct answer. And each guess is independent of the other. So the questions aren't related to the other ones. So just because they guessed the first one doesn't make them more likely to get the second one right. Okay. So first thing we want to find out, what's the probability of getting a correct guess on just one question? What do we think? Probability of getting a correct guess on just one of the questions. 1 out of 4. So because each question has 4 possible answers, the probability of getting a correct guess on one of the questions is 1 out of 4. Perfect. So that means the probability that you guessed incorrectly has got to be 3 out of 4. What's our n for this problem? 7. So in this problem, we're talking about 7 multiple choice questions. For the one that she did with you, I think there were 10. So the n for hers was 10. The n for mine is 7. We got 7 questions. Okay. We need all 3 of those numbers in order to be able to use our binomial theorem. So I'm going to write out the formula again. We had the probability of k is equal to n choose k times the probability of a success. That was our p raised to the power of that k. And then I use q, but you could use 1 minus p if you'd prefer for the probability of a failure. And that's raised to n minus k. So there's our formula. All right, and so it says, what is the probability that a student guesses exactly 2 correct answers? So they had 7 questions and they get exactly 2 of them right. That means we have the probability that k is exactly equal to 2. So in terms of how we're going to put that into the formula, the n was 7. That goes at the top. The k for this one is 2. So 2 goes at the bottom. So we're writing 7 choose 2 times the probability of getting a success on one of the questions. You guys told me that was 1/4. And we always raise that to the power of the k, which in this case is 2. And then we multiply it times the probability of getting a failure. You guys told me that was 3/4. And we raise that to the power of n minus k. So we're going to put 7 minus 2. That's the setup. Off to the side, I need to go calculate what 7 choose 2 is. 7 choose 2 is 7 factorial divided by 2 factorial times 7 minus 2 in parentheses with the factorial on the outside. So that's 7 times 6 times 5 times 4 times 3 times 2 times 1 in the top. And then we've got 2 times 1 for that 2 factorial. And then 7 minus 2 factorial is 5 factorial. So we have 5 times 4 times 3 times 2 times 1. And so when I did this on Tuesday, I said it's sometimes like helpful if you cancel stuff out. So we've got a 5 and a 4 and a 3 and a 2 and a 1 that can cancel. So we have 7 times 6 in the top divided by 2 in the bottom. So that's 42 divided by 2. So that comes out to be 21. So in our formula, that part right there is 21. times 1/4 squared, that's 1/4 times 1/4, so that'd be 1/16. And then times 3/4 to the 5th power. 3/4 to the 5th power means we've got 3 to the 5th power, which is 243 in the top. And we have 4 to the 5th power in the bottom, which is 1024. So usually on the test, you're like leaving your answer back up here. But since we're actually talking about a test here, I want to see what's the probability that this person guesses exactly 2 correct answers. I want to know. All right. So we're going to do 21 times 1 times 243. So we get 5,103 in the top. 1 times 16 times 1,024 gives me 16,384 in the bottom. So if I simplify that, 5,103 divided by 16,384 comes out to be 0.31 approximately. So student has no idea how to do any of these 7 questions. The probability that they guess exactly 2 of the answers correctly is 31%. So by chance alone, they can get 1/3 of the problems almost correct. Okay. What does that mean as an instructor? That means that we often have scores below which we go, that could be based on chance. So someone's like, oh, well, you know, I got 1/3 of the questions right on the multiple choice test. And we're like, did they get 1/3 of them right because they knew how to do 1/3 of them? Or did they guess really lucky? Okay. But we also can start detecting cheating in some cases. So I'm almost out of time. I will fill in the rest of them for you, but I'm going to actually skip down to the last one. And I promise I'll fill this one in. But this one's the most interesting since I only have a few minutes left. Let me tell you why this is interesting to me. I've been a teacher for a very long time, and I've had a lot of people where I'm like, I think you cheated. And they're like, no, I just got lucky and I guessed all 7 of them right. Let's find out the probability they guessed all 7 of them right. Okay. Probability that K is equal to 7. In terms of our formula, that would mean that you had 7 choose 7 times the probability of a success, you guys told me was 1/4 raised to the power of 7 times the probability of a failure, you guys told me was 3/4. And we raised that to the power of 7 minus 7, which means that's going to get raised to the 0th power. Here's a hint. We could go through and do 7 choose 7 using the factorial thing, but here's the good news. If the numbers are identical, it always comes out to be 1, I promise. So this piece right here is 1. If the numbers are identical, that comes out to be 1. So we have 1 times 1/4 to the 7th power. So that's 1/4 to the 7th power, which is 16,384. And then 3/4 to the 0 power, anything to the 0th power is just 1. So we have 1 times 1/16,384. That's just 1/16,384, which as a decimal is approximately 0.000. Let's see, I got one more 0 in there, 4 zeros. So when they tell me, I guessed all 7 of them right, I didn't cheat, and I go, no way. Or you better go buy some lottery tickets, because you're the luckiest person I know. very unlikely that you could by chance actually guess all 7 of them correct. Now, if you knew which, like on some of the problems, you could narrow it down and you were like, well, I know it's not that one or that one, so now I'm guessing between 2, that completely changes this problem. But if you're completely guessing all 4 of them, all 4 answer choices are equally likely for you to pick, then that's the probability that you would get all 7 right if you were just guessing. I promise I'll go back and fill in this one and I'll scan it into Canvas. Thank you guys. I know it was a little math heavy today.